When we first began our discussion of the reactions of alkyl halides, I mentioned that substitution and elimination could be in competition with one another. So to end our discussion of substitution and elimination reactions, we're going to think about how we can choose between SN1, SN2, E1, and E1 mechanisms when we are predicting the products of a reaction. Let's talk about that first, and then we'll talk about if it matters. But spoiler alert, yes, it very much matters. So first of all, we need to decide, well, is it going to be a substitution? Or is it going to be an elimination? If it's an elimination, we're probably going to see the more stable alkene. So I chose to deprotonate to make the disubstituted alkene rather than the monosubstituted alkene, even though we could have, right? And then you can think about the times where you can get the less substituted alkene on your own. So first of all, we have to decide, is it going to be the substitution product or is it going to be the elimination product, the alkene? And then as far as does it matter, let's say we see the substitution. Does it matter if it's SN1 or SN2? Well, yes. Imagine that this is a chiral alkyl halide. If it proceeds by an SN2 reaction, what would we observe? Inversion. If it proceeds by an SN1 reaction, what would we observe? Racemization. So we would see both enantiomers of the product because it goes through that achiral carbocation intermediate. When we were assessing the relative rates of SN2 and E2, we used this good, fair, poor method. And this just is a way to let you compare the rates of each of the reaction mechanisms. And then you're going to choose the faster one. And the faster one is the one that is going to be observed. You know, more than one might occur, but you're going to observe the one that's faster. And I have tried to distill this to the most important factor that affects each rate. Of course, there are many factors that affect the rates of each reaction. So for the SN2 reaction, the rate is little k times the concentration of the alkyl halide times the concentration of the nucleophile. Both of these species are involved in the rate determining step. And so the nucleophilicity matters of the nucleophile, the leaving group, stability matters, and the sterics of the reaction matter. And so when I say sterics of the reaction, I'm really referring to the substitution pattern of the alkyl halide. So how many other carbon atoms are on that alpha carbon, but also, you know, how bulky is the nucleophile. So we're going to have a fast rate of SN2 when the alkyl halide is methyl or primary. So for example, if you had methyl iodide, that would be a great SN2 substrate, or say ethyl chloride, that would be good too, because you have a primary alpha carbon or a methyl alpha carbon. So it's easy for the nucleophile to get in there and attack. Now you'd have moderate or fair rates of SN2. Let's say if you had 2-bromopropane, where the alpha carbon is secondary. Okay, so when you have a secondary alpha carbon, it's going to have a slower rate, but it'll be okay. Well, it's fair. And then finally, you're going to have slow or no rates of SN2 when you have a tertiary alkyl halide, such as this one, or when the nucleophile is bulky. So if we think about what's meant by that, I have given you an example. It's potassium T-butoxide. So this is our quintessential bulky base, but it can also be a nucleophile, and it's bulky. It's hard. It is difficult for it to attack. Think about it. Trying to get in here and attack that alpha carbon. That oxygen is surrounded by these methyl groups, and so that really slows it down. So when you have a bulky nucleophile like this, you are not going to see a very fast rate of SN2. It'll be pretty poor or slow. Now let's transition to thinking about E2. So the rate law for E2 is pretty similar to the rate law for the SN2. That's why they both have 2 in their names. It's the concentration of the alkyl halide, but this time instead of acting as a nucleophile, whatever your species, electron-rich species is, it's acting as a base. So you will have a good fast rate of E2 when you have a strong base. So E2 reactions require a strong base. Of course, you also need to have a good leaving group. You need to have a beta hydrogen to deprotonate, all of that. But also, most importantly, you need a strong base. If you don't have a strong base, it's not happening. As you recall, that base gets in there and it deprotonates the beta carbon, eliminating the leaving group. And like I said, you definitely need to have a good leaving group. So you'll think about those things as you're evaluating reactions. But a place to start is the base strong? So you will have a good fast rate of E2 if the base is as strong or stronger than hydroxide. And you want to look at the conjugate acid pKa. If the conjugate acid pKa is greater than or equal to 16, like it is for water, then you'll have a good fast E2. If the conjugate acid pKa is between that of hydronium and water, so if it's between 0 and 16, then you will have a fair E2. And if the conjugate acid pKa is less than 0, meaning that it's a strong acid, then you have a weak base, right? These are the conjugate bases of strong acids, so they are weak bases, and you're going to have a slow E2. Now, SN1E1 reactions, these require a stable carbocation. So you will have the best rate of SN1E1 when you have a tertiary halide or a tertiary tosylate. And this is because you make a tertiary cation, and this is the most stable. So you can have a tertiary halide, or if the cation is stabilized by delocalization of charge, so resonance, then you also have a good stable carbocation. So we can imagine this carbocation, let's do a tosylate. So if this tosylate leaving group leaves, you might say, hey, but that's secondary. Yes, it is, but you also have an empty orbital adjacent to the pi bond. And so you can draw a resonance structure and show how this carbocation is stabilized by delocalization of charge. So this one would also make for a nice, fast E1 SN1. You will have a fair SN1E1 if your halide is secondary, because that will lead to a secondary cation, and then a slow or no SN1E1 if you have a methyl or if you have a primary, because these will form methyl cations and primary cations, which are just not stable. So you won't see any SN1E1 for those. Now, SN1E1s do typically occur together, but if you want to ensure E1, you can, say, treat an alcohol with concentrated sulfuric acid, or you could use phosphoric acid. And then you'll exclusively get the alkene via E1, which we talked about in that lecture. Okay, we're going to practice. These are some simple examples. And when I say simple, I do not mean easy. What I mean is that the molecules are small. But you're going to go on and look at more complicated molecules when you do your practice problems. And you just, every time, just keep it simple. Stick to the basics. You need to identify the alpha carbon. And to evaluate both SN2 and SN1E1, you need to think about the substitution pattern of the alkyl halide. So we have a secondary alkyl halide, right? That alpha carbon is bonded to 2 other carbons, so it's secondary. And we have the same alkyl halide for all 3 reactions. So if we want, we can just go ahead and evaluate all 3 for SN2 and SN1E1 right now. So secondary alkyl halides are fair for SN2 because it's kind of hard for the nucleophile to get in and attack that alpha carbon. And SN1E1, this is also fair for secondary halides because this forms a secondary cation, and they have intermediate stability. They're higher energy than tertiary, and we saw they're prone to rearrangement. So you have a slow SN1E1, not a slow, sorry, a fair SN1E1 for secondary alkyl halides. Let's evaluate E2. E2, we look at base strength. So, and I specifically want you to write out the conjugate acid and think about its pKa. So the conjugate acid of cyanide is HCN, and it has a pKa of about 9 to 10. So that is in between base strength of water and hydroxide, which is fair for E2. Now, it tied. That's obnoxious, right? Well, we just need to just look around and think about what's going on here. So cyanide is an excellent nucleophile, and that will help us favor SN2. So this is an excellent nucleophile. That will favor SN2. Remember, SN2 has a rate law that involves a nucleophile. SN1E1 does not. So it does not really matter how good of a nucleophile you have for SN1E1 because it's not in the rate law. But because cyanide is an excellent nucleophile, that will favor the SN2 here, and we will see the substitution product, the alkyl cyanide. All right. And then, of course, I will mention if this were chiral, you would get inversion. And it would be important to realize that this happened via SN2 because you would get inversion. So I'm going to do a slightly more complicated example up top. Still a secondary alkyl halide. I just kind of threw another methyl group on the end here. And you would get inversion of stereochemistry if we went by SN2. All right, awesome. Let's take a look at the next example. So the difference in the next example is that we have hydroxide now, and hydroxide is a strong base. We've defined it as a strong base for E2, but we can also just write out its pKa, the pKa of its conjugate acid, which is 16. And so let's go ahead and draw in the beta hydrogens, because we know it's going to do E2. Strong base, good for E2. These beta carbons are the same, so we'll just pick one, and we will eliminate the hydrogen. Okay, and you might write it out in a nice zigzag form, but those are the same things. Oops, leaving group leaves. Sorry, got excited about that. All right, we don't need to show the inorganic products here, but we do have bromide as well, and we had bromide and leaving group for this first reaction. So last reaction, now we have water. So cyanide was a fair base, and so we saw SN2. Hydroxide was a strong base, so we saw E2. Water is a weak base. Its conjugate acid, pKa, is -2. So it's a strong acid, which means that, so hydronium is a strong acid, so water is a weak base. So this will be poor for E2. So we've ruled out E2, but it's a tie between SN2 and SN1E1. Now, water is a weak nucleophile, so you might go with SN1 here. But again, this is a pretty tough call. But no matter which mechanism it goes by, you're going to have the same alcohol, the same substitution product. The only way to know for sure if this one goes by SN2 or SN1 is to either do a kinetic study, so vary the amount of water and see if it changes the rate. If it does, it was SN2. If it doesn't, it's SN1. Or to start with a chiral alkyl halide, as I have written up here. And if it goes by SN2, you'll see inversion, where you started out with your stereocenter out and it ends up N. And if it's SN1, then you'll get racemization. So SN2 inversion, SN1 racemization. So you would definitely know from the stereochemical outcome if you treated this chiral alcohol with water. But in this case, either way, the product looks the same. So let's now take a look at another set of alkyl halides, and I would really like for you to try this on your own before you listen to me go through the answers, which I am about to do. A good place to start when you're solving any predict the product questions for the rest of your time in organic chemistry is to label functional groups. So, and then for alkyl halides, also the substitution pattern is really important to have. So all of these are tertiary alkyl halides. The rate of SN2 and the rate of SN1E1 depends on the substitution pattern of the alkyl halide. For SN2, that's because the nucleophile has to get in here. If it's a tertiary alpha carbon, that's super difficult for the nucleophile to do. So tertiary alkyl halides have poor rates, really slow, basically no SN2. But tertiary alkyl halides are great for SN1E1, and that's because they make tertiary carbocations, which are relatively stable as far as carbocations go. So all of these reactions, all of these alkyl halides here, which is the same one, this tertiary alkyl halide will have a good rate of SN1E1. So now all there is to do is to see if E2 will outcompete it or not. So think about SN1E1. I said it has a good rate, but you still have to kind of wait for this bond to break to form the carbocation. And if you have a strong base, you're not going to have, the molecule is not going to just sit around and wait for that bond to break. The base is going to deprotonate something. So we can see that in our first example. We have hydroxide, which is a strong base. So this has a good rate of E2, and you're just going to see E2 because proton transfer reactions are facile. They're easy, they're fast, especially when you have a strong base like this. So we are going to see E2 elimination here to form this alkene and the bromide leaving group. Okay. So let's look at the next example. So the next example has methanol. Methanol is a weak base. It is the conjugate base of a protonated alcohol, which is a strong acid, just like hydronium. So this is a weak base. So this will have a poor rate of E2. So in that case, we're going to see SN1E1. The substitution product will look like this. Okay. Let's go ahead and do the mechanism because we're still just getting used to SN1E1. So we have heterolysis to form the tertiary cation. That's our electron poor species. Methanol, it's so, weak base, weak nucleophile, but the carbocation is really reactive. So it does donate electrons to it. That generates a protonated ether that looks like this. That has a pKa of -2, so that is not going to just sit around there. So another molecule of methanol comes and deprotonates it to make the substitution product, which in this case is an ether. Awesome. All right, let's try one more. So we have same alkyl halide, we have water. Water is a weak base. So this reaction will also have a poor or slow rate of E2. So we'll see SN1E1. And so you'll see the substitution product going by the same exact mechanism as I showed you for the previous example. Now, SN1 and E1 do happen together, so you should also predict this minor product of the E1 elimination. So I'll show you the E1 elimination this time. So that same first heterolysis step to form the carbocation and the leaving group. But this time we deprotonate one of the beta carbons. All three of these beta carbons have hydrogen and all three of them are the same. So I'm just going to choose one. Now water is a weak base, but a carbocation is a really high energy. So water reacts with it in an electrophile elimination step to generate the alkene and hydronium. All right, but the E1 is typically the minor product here. All right, so I think it was easier for the tertiary alkyl halides because SN2 was out of the picture now. We were not going to be predicting SN2 for a tertiary halide. So really the question became, do I have a strong base? If I do, then it'll undergo E2. If I don't, it's going to undergo SN1 E1. So that's what we saw here. So summarize and reflect. Please don't skip this step. And we have now achieved our final learning goal for the substitution and elimination reactions, which is to predict between all four mechanisms when we are given some alkyl halide, alcohol, or alkyl tosylate under specific reaction conditions. So we are now able to decide which product, substitution or elimination, and we know by which mechanism it goes by using the good, fair, poor, and then a little bit of our chemical intuition when there's ties or when there's special circumstances. Okay, time to practice.